Good afternoon, everybody. Welcome back to MI 210. Our webcast this afternoon is the lab session for the individual and population BK modeling section. I posted a quick poll before the class today just to get an idea of how things are going with the homework problems, who's had a chance to try this yet, and also to get an idea if there are technical difficulties. Looks like we had about a third of the class hasn't had a chance to do the practice problems yet. About a third of the class did the first problem, and then the rest are a mixture here between technical difficulties and difficulty understanding code. Those of you that ran into technical difficulties, please be aware that Joe Hebert had posted some instructions on how to report those technical difficulties, whether it's a problem with your with the browser recognizing the web page or the web page not loading completely, whatever it is. We want to be aware of those, and we should be able to help you solve it as well, or to make whatever changes are necessary. But please follow the instructions that Joe provided if you run into real technical difficulties with the browser or the CIMI interface, and let us know. And we've asked for some specific details there, like the type of browser you're using, the version, the operating system, the particular task you were trying to do, and the error message. But it looks like most of you were able to get at least something up and running. Maybe you ran into some difficulties in understanding the code, but that's okay. That's what we're going to review today. Okay, so I'm going to turn off the poll. And I'll share results with the group here. So nobody got through everything, but the majority of the folks got through the, or the largest response here was the completion of the first problem. So that's good news. Those of you who didn't try yet, if you're, and it's fine if you want to just audit the class and not do the hands-on, but if you are interested in doing the hands-on, please give it a try so that we can work out any technical difficulties in the course now before we get heavier into the hands-on work. Okay, I'm going to close this up, show my screen. And so now you should see my screen with the practice problems outlined. So first I'll start by reviewing any questions on the question board. Nothing yet, but feel free to post questions there. And I'll pause as we make it through the examples and try to answer those questions. We also had a couple of questions come across the discussion board throughout the week, and my answers are posted there. Nothing really really all that complicated. It's just a couple of clarifications here and there. So please take a look at the discussion board. But if anybody wants to bring another question up during class right now, please just post it to the question chat box on the GoToWebinar control panel. Okay, let's dig right into our practice problem. Remember, at the end of class last week, we had gotten through problem 1 with our first attempt at the model, and we made some conclusions at the end about some findings, some things that we thought were interesting. Let's go back and review that. I'm going to pull up CIMI. And we'll go right to the enzyme problem. Let me increase the screen size for you. Okay. And the controlling script for all of this is something called ens.r. And this is the standard that we're going to use throughout the course, is that we'll have an R script. Usually it's the name of the problem .r. That will be the controlling script that helps us to do everything from data assembly, plotting, running non-mem, viewing the results, and so on. So that's what we're going to open first. And remember, you can click the edit button on the right hand side. If you hit the control or command key, it will open in a separate panel, a separate tab. And let me expand this as well. Oh yeah, I should also point out that our technical support, Jeff Hall, has adjusted and corrected some of the help file problems. If you recall, before we weren't able to access MI Funds help. Now you have MI Funds help. In fact, why don't we take a minute to look at that before we get into the problem. If you click on the MI Funds help, you'll see a variety of functions here. Now that's kind of overwhelming. You can search through that list and click on each one and understand what they do, but if you want a little more guidance, just click on the MI Funds package, and there's a nice sort of question-based lead-in to the help here. You can say, well, I want to do one of these tasks: prepare data, model data in non-mem, conduct simulations, create diagnostic plots, generate report material, perform file system tasks, or see available list of functions. So that helps you hone in on the help file. And for example, we might want to say, I want to model data in non-mem. And there's a variety of functions here that will help us to do that. One is to run non-mem, and that's the non-R function. We're using that. And here's the description of non-R. There's a lot of options here. I've given you just the basics in the course scripts, but there's a lot of flexibility here. If you run in different types of environments, on a standalone machine or a grid or different types of non-mem run commands, it's a very flexible command. It's also designed to work with a program called Sun Grid Engine, which is a distributed computing management tool that's useful for running on a grid. But you can also just make a very simple call to non-R. But this is how you'd find the help on these functions, and we can just go back, look at other functions, generate a combined run log. This is a useful tool, and so I invite you to play with that, to try some of these functions with your own analyses, and we'll certainly use these throughout the course. Okay. And like I said, you can always go back and just search on a keyword topic or a letter that illustrates the particular topic that you're looking for. All right, that's MI Funds help. The other help pages are the non-mem help files and the R help files, as well as help for how to use SIMI. Those are all current now, and those links are all active. So let's get back to the problem at hand. This is the enzyme kinetics problem, and remember what we did initially here was we ran a model for this analysis that was based on a Vmax or a saturable process type model for this enzyme activity data. When we were in class, we looked at the data, we identified an error, and we commented out that error. We created a new data set, then we ran that model. So let's look at the model that we ran and the diagnostics just to refresh our memory. So there's 1.ctl, that's the original model. I'm not going to edit it, I'm just going to show you right now. So the usual stuff here, $prob, input data, I think that's probably clear by now. The key points are that we used inter-individual random effects on Km and Vmax, both of those entering in an exponential fashion. And we used an additive residual error. The theta estimates were bounded at a lower end of 0 with initial estimates of 20 and 120. Omega was a diagonal matrix, and sigma was just a single element here, an additive variance of 10. Okay, we used method 0 with post hoc, and we tried to get the covariance step to run. So let's see what happened to that run. If we go to the directory that says 1 here, and we look at the file 1.lst, it reiterates the model above us, and then tells us about our license and a lot of options that we use. Let's get down to the interesting stuff. Here we go, monitoring of search. I'm just going to make it a little bit smaller. we saw here that the parameters and the gradients were starting at a large value, and the gradients were decreasing over time. So that's, after 10 iterations, they've dropped from 10 to the 10th to 10 to the 1st, and then another 10 iterations it dropped even further. Looks good. None of these gradients are zero. Actually, we end up with a zero gradient at the end for this parameter, and we'll see why. But the two fixed effects parameters, the first two parameters, theta 1, theta 2, that's Vmax, I'm sorry, Km and Vmax. Those gradients look good. We do have a zero gradient here at the first element of omega. Then the next two are okay. So when you end up with a zero gradient, or you see a zero gradient throughout the search, that should always flag your attention. Let me I'm sorry, I'm just getting a message here that the screen's not showing. I don't know, Joe, if you can confirm that. I do have my screen enabled for screen sharing. Anybody else having the problem? Okay. Well, it looks like a few of you can see my screen, so it looks like we're on. Just try to make sure you have the correct window active on your screen if that's not happening. Okay, sorry for the interruption. Let's move on. I was talking about zero gradients. A zero gradient, well, what does that indicate? When the gradient of the model prediction with respect to the parameter is zero, that means it's not changing. And if you happen to have a zero gradient from start to finish throughout an iteration search, you're really seeing that a parameter has no impact at all on the prediction, and that usually indicates that you have a coding error, a data assembly error, something like that, where the parameter is not participating in any part of the model prediction. So that's not a good thing. That's an error, and that has to be addressed. Sometimes you end up with a zero gradient during the search, just intermittently, or at the end of the search. And that would happen if at the end of the search. That usually happens when you've hit a boundary or the parameter's not moving for some reason. And you'll see here in our output, we see the message, error message, parameter estimate is near boundary. So we saw why that was last week, and I'll just remind you why. This is one of the variance terms that was approaching zero. The other error message here is that this must be addressed before covariance can be implemented. The covariance step, or the step that is used to generate the standard errors of the estimates, by default it's only implemented conditional upon a successful minimization with no boundaries on the parameters. Well, if you scroll down, you'll see the final estimates here. We had a Km of about 46, a Vmax of 105, but this is the culprit here. So omega 1,1, which is the variance of eta 1, that's the variance on Km. That's approaching zero, and it just so happens that zero is the boundary condition for a variance term. The variance terms can't be negative, so their lower bound is always zero, and that's what the monitoring of search message is telling us, and that's what that zero gradient was telling us. So we're into that problem. Otherwise, the output here looks decent. Just to remind you again, we looked at some diagnostic plots. Let me back up a directory, and we'll look at diagnostics. And so you see the red line here is the fit through the observed data. It looks like we're going right through the middle of the data. That's very good. We do see increasing variability as the response increases. And so we have to think about how consistent our variance model is with that. But here's the observed versus predicted, population prediction on the left side, individual prediction on the right side. Looks very good. The residuals versus pred, though, this is a plot that tells us about our strategy for weighting the data. And the residuals versus pred shows us a heteroscedastic variance. Now, I didn't create it in this plot, but we could have created a weighted residuals versus pred. And in fact, I'm just going to do that right now to show you what that would look like. Now keep in mind, or at least think about, what should the weighted residuals versus pred look like? The weighted residuals versus pred ideally should be a constant band of points across the range of the prediction. So all we need to do here is change residual to weighted residual. Okay, add the 0 line, and that looks good. So I'm going to, I think everything's still in memory in my R session here, but just for the heck of it, I'm going to import the data again and create these plots. And let's see what happened on the console. Wrong one. Oh, didn't like that. One thing with the graphical interface here on CIMI is sometimes if you try to highlight too many rows of text at once, try to execute too many rows, there's a read error and you end up with some difficulties. So another solution is just to step through it. So evaluate that piece and we'll just check. I went down to okay. I need to import the data first, that's why. Need to run the model. We'll start from the top. When in doubt with R, make sure you start from the top and execute everything you need. It's a good habit when you're writing R scripts to make scripts that are completely self-contained, so that they don't rely on the byproduct of a separate script that you might have used elsewhere. Okay, then we're gonna okay, so that's working all right, and we'll come back to running nonmem now. So this is the very simple nonmem command or non-R command. 1 is the number of the control stream. The command we defined above, that's the path to the nonmem runtime command. Grid equals true because we are running in a grid distributed environment here, and we're not going to run the default diagnostic plots. So that's false. Okay. Okay, job submitted. And you see here it says run 1C, run 1E. That's because we separate up the compile and execute pieces. With nonmem, every time you want to run a model, you first have to compile that code. The code is compiled on the fly, and so there's a compile step that's built into the script that runs nonmem. Okay, and now let's do some plotting and turn off the graphic device. Sorry about that. Let me try again. Okay, so once that device off command has been executed, you know that your PDF file has been created. And we can come back now and look at the diagnostics.pdf. This is for run 1. Yeah, I sent it up a directory. Okay, so there's this first plot. Here we go. No, we forgot to put the 0 line. But what you see here on the bottom 2 plots is something that should immediately raise your attention. The left-hand side, residuals versus pred, should show the pattern of variability in the data. That should show that cone-shaped pattern. But the right-hand side, weighted residuals versus pred, that shows us the model fit with the weighting scenario or the weighting strategy included. And an appropriate weighted residuals versus pred plot should have a constant variance look to it. It should not look heteroscedastic like this one does. That's because we used an additive model for variance that's also heteroscedastic. So we've got a change to make there. Okay. Other than that, the fit looks pretty good. No, there it is. So let's go back now. What we're going to do is create a new control file. So what we can do is we can take 1.ctl and edit that one. And then we'll just call it 2.ctl and hit save. Make the window a little bit bigger. Number 2. And what we're going to do here is change the 2 things. We're going to change the residual variance model. So what should we use? Well, we should use something that's got the heteroscedastic nature. So we could use a proportional model, something like this. So activity, the prediction, plus the residual error that's proportional to the predicted activity. So now we have a proportional model. We've got we already know that the estimate of this variance term is being driven to 0. So what we could do is eliminate that from the model by typing 0 fix. So the estimate was approaching bound of 0. So we'll drop it out of the model, see if it helps our boundary problem. And up here I'm going to say weighted residuals plots indicated that additive model was incorrect. Okay, does everybody understand why we made that decision? And then we changed it from a additive to a proportional, so 10 now would be 10 times constant. That's the variance of a proportional. That's way too large. So let's use something like 0.04, which is about a 20% coefficient of variation. We'll try to run now. We'll save the model specification file, the table file, we'll call it number 2, and we'll run covariance. And I'm going to save this as 2.ctl. I thought I did that, but I'll do that again. Save. And let's go back to SIMI. We should now have we should have 2.ctl, but it didn't save it correctly. Okay, our save function doesn't seem to be working here today. Let me try that again. There it is. I just needed to refresh. Sorry about that. So there's 2.ctl, and that does include the changes we just made. All right, so we'll go back to the R script now. And to run 2.ctl, we can simply copy the non-R command. Not the whole thing, just the non-R command. And I'm going to delete this code at the end. Now the non-R command will just call number 2. And what we can do is we can actually copy all of the diagnostics data here. So let's just, and later in the course we actually automate this in more detail, but I just wanted to show you that you can do this manually. So we have the non-R command here. This is, we can put a comment up here, you know, run with omega 1 fixed to 0 and proportional residual error. So that's what that'll do. And then all you got to do here is change the name of your table file, 2.tab, and the rest of the script is unchanged. Okay. So what I did is I copied the piece and pasted. You can always rerun in the same place, but it's nice to every time you make a change or rerun something is to just keep the script moving forward. That way it creates a log of what you've done. So we'll save that. And now we'll run non-mem on the second model. And it executed the compile step and the executable step. Okay, so let's go back now to run the diagnostics. We'll import the data. Evaluate that. And then we'll plot and close the graphic device. Sorry, I tried to do too much there. Try that again. This is a known bug in the CIMI interface, and the workaround is to just execute a smaller number of lines each time. The next version of CIMI actually addresses this. Okay. All right, so we should be good to go. Let's look now at our diagnostics. Sometimes you need to refresh. There's model 2. Let's look at the output file, 2.list. I'll expand that. So now here's monitoring of search. We've simplified the model because we've removed the one of the variance terms, and we see the gradients starting out in some relatively high number here, becoming smaller in the next step and smaller at the finalization. Pretty quick here. No problems with boundaries. No warning or error messages. The minimum value of the objective function is 627. We see that Km is about 37 and Vmax is 96.4. Those have changed a little bit by dropping the variance term. And we have a variance estimate for the inter-individual variability on Vmax. And we have an estimate here of about 0.01 for the residual variability. Then we also get standard errors of the estimates, because the covariance step was run now. And with the standard errors, we get 2.95 for the first parameter, That's on a value of 36. So that's less 37. So that's less than 10% error. That's very good. 3.23 on a value of 96. Again, very small, like 3% error. So that's very precise. Of course, these are simulated data. The interindividual random effect is 10 to the minus 3 here. And so is the final estimate. So that's not as well estimated. And you'd expect that because we only got 20 individuals or 20 experimental units here. So that's expected. And then we have the residual random error, which is 0.01. That's a standard error. And the final estimate is actually 0.1. So that's not so well defined. Well, about 10%. So altogether, decent fit. Let's look at the diagnostics. Back up one step here. There's a file called diagnostics.pdf. And the way this file works now, it's actually captured the prior run here, but here we see the diagnostics between the pred and the IPRED. Those are about the same as before. But here's the real change. Residuals versus pred. You see the heteroscedastic nature of the residuals versus pred, which is fine because that's telling you about the variability in the data. But then when we go to the weighted residuals versus pred, we should see that pattern disappear and have a more constant variance, which is what we see. So now the model looks a lot better. We've satisfied the assumptions there of a constant variance after appropriately weighting. The other thing to look at then would be the eta distributions. We can go back and to our R script. And I'll just add another plot here. Just a single 1 by 1. And this will be an eta versus eta plot. Well, first we want to make sure that we have the etas in the data set, so we might try something here. I forgot what we had included, but we can just look at the top of our data file here. Yeah, we don't have the etas in our table, so we're not going to be able to plot them. So we could go back now and run a model specification file to do this, or just rerun the model. And since it's a short run, and I want to spend some time on the other problems, I'm going to just go back and run it with by editing model 2 and adding the etas to the control stream. Okay. Eta 1 and eta 2. These are recognized values. In this case, eta 1, what's the value going to be? Should be 0 throughout because we fixed it to 0. But we can still look at the distribution of eta 2. So we'll save that. And go back here. I'm going to add one more plot. And what I'm going to do now is eta distribution. And we'll just use the histogram function for that. Okay. Save that. So we've got to go back and run the model because if you recall correctly, we have forgotten the etas. So let's evaluate that. Job is submitted and it's running. Here it comes. Okay, great, it's completed. Right now we're doing this all interactively because these are short runs, but there are options with the non-R command to actually run a script that happens after the run is completed. In an automated way. Okay, let's see. Looks okay. Well, I asked for a histogram of eta 1, didn't I? Well, that's exactly what I got. Eta 1 is 0. There's no eta 1. So let's redo that and get the histogram of eta 2. And let's just create a separate file here. PDF. When we're creating PDF files here in R, you need to open the file, write to it, and then close the file. So let's just execute that. Refresh the window. There's etadist. And so here's our density plot for the individual etas. Now, remember, we've only got 20 experimental units here, so it's difficult to get a full density. But it's sort of centered at 0. It looks almost multimodal here. So you might conclude here that our description of the inter-individual variability is poor. It might be a violation of our assumptions. The problem is that we don't have enough individuals. So this is a good illustration of the problem of trying to estimate inter-individual random effects when you don't have enough individual units. And that's why the standard error for that parameter was large too. The standard error for omega 22 was quite large. All right, but that's a basic idea. So this is the best we can do with this model. It doesn't mean that because that eta distribution is problematic doesn't mean we should throw away the model. It's just telling us that we don't know that inter-individual variability all that well. The model for the typical value effects, the fixed effects, seems to be performing well. So that's that example. Let me pick up on some questions here. Okay, so there's a question about an exponential error model. Do they need to do log transformation in M7 or use the original data? You could code an exponential error model. Let's look at the control stream here. We could code in this residual in a different way. I'll just comment it out. We could write ACT times exponential EPS1, which is the same, or seems like it's the same, as log y equals to log activity plus EPS1. But in fact, these are different. Because of the first order approximation that's made in non-mem, in the at least in the classic non-mem estimation methods, this first residual model is different than the second because the first order expansion of this function results in a proportional model, like the one above it. So you could code that, but what you're really getting is a proportional model. Okay, this is actually is proportional model with FO, and this is FOCE, Laplacian, any of these Taylor series expansions with, we'll just say with likelihood approximation. But on the other hand, if you log transform both sides, so we have the log of the data, so let's say y was really the log of the data, then you could write something like the right-hand side here, the log of the prediction plus epsilon. That gives you a true log normal distribution. That's how you can get the full exponential residual error. There's a question about estimating covariance between eta 1 and eta 2. In the last example, eta 1 and eta 2 weren't uniquely identifiable. We'll try to estimate the covariance in another step, but remember that eta 1 variance was approaching 0, and we ran into the trouble with running a covariance step there. That was a clear indicator that we needed to eliminate that parameter from the model. When you're over-parameterized in the omega matrix, that's what happens. You hit boundaries, the covariance step won't run, and sometimes you need to pare it back. But that's okay. You'll learn that from the error messages and looking at the diagnostics and the gradients. All right, so that's the end of this problem, which I think is about as far as most of you got who did the examples, at least from the poll. I'm going to take you to the next step here. We'll work on the the QT and the AST data sets. Sorry, I'm just reading one more question here. Eta 1 in run 1 hit the boundary, and then we fixed it to 0. Could we change the variance model from exponential to some other structure to solve the problem? You could try that. You could try that. It's not likely to help. You know, it's one thing to have a slightly wrong variance structure, and you know, with only 20 individuals, this analysis is probably not going to be too sensitive to the distribution of the etas anyway. What that was clearly showing us, since it was so small, 10 to the minus 6, it was pretty clearly telling us that that under this design, the variability between subjects in KM is something that can't be estimated. Doesn't mean that there is no variability between subjects in KM. It's just that could be the case, but it also could be the case that it's just a poor design for that particular purpose. All right, let's close this up. Yep. Leave semi and ends.r. We're done with that. Go back to our home page. Let's look at the QT problem now. So the QT, open the R script. And this is kind of a very concise piece of code here. I'll insert some comments as we go through the class. But we'll have to set the example to a different directory now. And so we could run, let's just run down to here. I'm not going to run none of them just yet. Okay, let's go back to the class notes, which will tell us. Which will tell us a little bit more about those relationships. Remember the QT data? Sorry about the scrolling here. I'll pull it back up. The QT data and the AST data were analyzed in the first chapter. Here we go. Here's the AST data, and here's the QT data. We got a relationship between delta QTC and concentration. So this is just the delta from baseline, and you see this sort of linear-looking shape. You might try a nonlinear relationship, but it looks pretty linear. When we look at the next example, AST versus DV. DV is the concentration here. You see something that looks increasing, but maybe not linear, although lots of variability out here. So we're going to look at both of these. Maybe they require different structural models. We'll find out as we get through the modeling process. So go back to CIMI. And we'll start with the Qt dataset. I've got a control stream that we can take a look at. Here's a Qt dataset. Ignore equals ampersand here. This is just indicating any line that begins with an alphabetic character is ignored. We're starting off here with a naive pool model. The reason I know that is because of the omega block. So it looks like we have a mixed effects model because we have an intercept plus a random effect, a slope plus a random effect. Delta QTC is just an intercept plus concentration times slope. Concentrations in your data set. And then we have the observed data equal to the DQTC plus an error. That looks straightforward with some initial estimates for theta. We don't have any bounds on these, although we could easily put bounds. But since it's a delta model, you know, we don't know if that intercept might go slightly negative. And the slope could be negative. Maybe the drug decreases QT length. So we don't necessarily need a bound on that. But then the omega block here is fixed. You can tell that it's fixed, even just one single instance of the word fixed, when you have a block matrix, will fix the entire matrix. And it's fixed to 0 because we're starting off with a naive pooled analysis. And we have an additive residual error. Okay, and then a bunch of stuff plotted. Let's go back to the R script. So the first non-mem run, I'm going to insert a comment here. One is a linear model, naive pool analysis. I'm going to show you how we can run these in a batch, but we'll run through each model first. So then we'll run number 2. What's number 2? Let's take a look. Save this guy. Two now is the same model, linear model, but we're estimating omega, at least on the diagonal here. And you know, just for the heck of it, let's make this a block matrix. So I'm gonna change that to omega block 2. Everything else will remain the same. Save that. Notice also that we're doing mixed effects model with method 1 interaction now. So this is FOCE with interaction. Unlike what we were doing before, which was FO method with a post hoc step for the individual estimation. Okay, so let's go back to our code here. Number 2 is linear model. FOCE interaction, and we're going to block omega. All right, and then while we're running them, let's look at number 3. Again, the same data set. But now we're trying something a little more complicated. We're going to try to estimate the parameters of an Emacs model. It looked kind of linear, but we'll try the Emacs model and see what happens. So for this, we have inter-individual random effects on an E0 and EC50 in Emacs. We write out that Emacs model, E0, the intercept, plus Emacs times concentration divided by EC50 plus concentration. That's our prediction for delta QTC. We're modeling that with an additive residual error We've got initial estimates on all the parameters. Now here it would be reasonable to put some lower bounds, because you have to have an EC50 that's positive. And there's no such thing as a negative concentration here. So for EC50, we can bound it at 0. Emax and E0, well, again, that's intercept and a maximum effect. If it's a negative effect on the drug, Emax could go negative. If that intercept was not quite at 0, that could also go negative. But EC50 should be positive. You'll notice there's a full block matrix now. That's going to be difficult to estimate. I'm sure this will not converge completely, but we'll try it anyway. So we'll save that guy. So 3 is the Emax model. FOC interaction, full block omega. So this is one thing you can do. You could start at the beginning by postulating a few alternative models, and that's what we've done. We've saved each one of these, and now we're going to just run them in a batch. See, the key here is that the first argument in the non-R command is now a vector, 1 to 3, 1:3. So that means it'll run every model from 1 to 3. So we can do that and click evaluate. And this will take a few seconds to run. Remember, we're running conditional estimation now, so that's going to take a little bit more time. Actually, it's going pretty quickly. A simple case. And we're just waiting for that last run to complete. Oh, it looks like it completed. Yep. So while that's finishing up, I'm going to look at one question here, maybe answer a question. In the QT3 example, are EC50 and Emax exponential more reasonable than additive? Well, that's a good question. The problem about using an exponential error, so let's go back to that model. Let's see, let's pick the number 3 control stream. Question is, would it be helpful to make these random effects exponential? Well, for EC50, I would agree, yes, because we want not only the population estimate to be constrained to be greater than 0, but the individual estimates as well. When you have an additive model like this, all you need is a large value of a large negative value of eta 2, and that shifts your whole prediction negative. The exponential model would have constrained that to be positive. Okay. Emax and E0 for this particular endpoint, since we're not sure if the drug increases or decreases QT, although you look at the plot and it's clear that it increases, you might want to still allow that flexibility. It could be physiologically realistic that the drug decreases QT, so the Emax might be a negative effect. And the E0, remember, it's a delta, and so if the delta is not quite at 0, it might be a small negative number. So at the individual level, you might want to leave that additive. But EC50, I agree with the idea that you might want to constrain that to be 0, not only by putting a bound on the population estimate, but also by constraining the individual estimates to be positive using the exponential distribution. Okay, we're running low on time here, and that's okay. We can pick this up in more detail next week. I'm just going to run a couple of plots so that we can look at that before we quit. So we'll read the data. And then let's actually, I might have already done these. Let's see if they're there. That'll save us some time. Diagnostics. No, I didn't. So we'll run each one. Okay. Still writing the file. Oh, it's because I'm looking in the wrong place. Sorry about that. Number 1, diagnostics, is over here. And so here's the dv-pred plot. Looks quite good. Residuals versus time. Solid around 0. Residuals versus prediction. Seems pretty consistent. Maybe a little bit larger variability at the high end. Weighted residuals, though, look pretty good. So the additive model that we use seems to be reasonable. When we look at the concentration, observed value and predicted value versus concentration, describes the data quite well. And then this is just an individual by individual plot of the concentration, the effect time course with both observed and predicted values. The low doses, you really can't see anything. It's just the higher doses that you can see, but pretty good concordance of the observed and predicted values. So that model does well. That was the naive pooled model. The difference here is that we don't get any information about inter-individual variability with the naive pooled model. So our estimates now are simply the fixed effects. And our slope's about 0.016 and then negative 0.089 is the intercept. And we have a residual error which really encompasses all of residual and inter-individual as well. So when we do the mixed effects model, you'll see that you see with the mixed effects model, first of all, it takes a lot more time to iterate. But now we have estimates of all of the terms in omega. And again, we're getting some problems here. I can tell that's a small estimate of the variance. We saw this comment up here. Maybe I went by too quickly. Parameter is near its boundary. Which one is it? Anybody guess? There's your zero gradient. So that tells you pretty clearly which one is problematic. And it looks like it was doing okay and then finally hit a zero at about the 15th iteration. So again, same sort of problem, and we could go on and correct that. So what I'm going to do here, since we're out of time, is give you an opportunity to play with this a little bit more. I will supply a heavily annotated solution set for both of these. And since we need to move on in the course, please work on these on your own. We can maybe take a little bit of time next week to discuss this, but I prefer that we maybe move the questions to the discussion forum, and we'll see some of these same issues as we move into the PK models, which we'll do next week. So before we sign off here, let me look to see if there are any last questions. Okay, looks clear. I'd like you to all try this, and again, if you're having technical difficulties, please let us know right away so that we can get everybody up and running. It seems like we've addressed most of the issues, but there may be a rare browser operating system combination out there that we haven't tested. All right, thanks for your attention, and please forward questions through the discussion board. We will pick up the class again next Tuesday, where we'll start to work on the population PK models. Have a good weekend.